on this default domain over here, I can insert a boundary. So by doing that, I can insert, for example, inlet, boundary type. I can choose between inlet and outlet, opening, wall, and symmetry. So this is an inlet. And then you can select the face that you want to set as an inlet. That in this case is this one. And hit OK. Then you can also set some boundary details. So in Fluent, we should set total pressure and total temperature. In CFX, we don't need to set that already because that information will be lost when we upload the case in Fluent. So we can just put like one dummy value here. It doesn't really matter. We are just setting like the inlet boundary condition there. And then we can do the same for, so insert, boundary, then outlet. We select the outlet, that is this face over here. Set one dummy value for the static pressure. And so we set also the outlet. Then, okay, I'll show you also for all the other boundary conditions. So this is the plate. The plate is a wall. So we select wall, boundary type, and we need to find that this one. So this is our solid plate. Then we can set also the symmetries, like the symmetry on the sides. There are these two surfaces. Show you. These two surfaces are our symmetries. So the flow there is somehow free to move. You can set them like symmetries because we are not interested in solving the flow in that direction. And then we can set the symmetry at the inlet. This is that this small surface at the inlet that we said that doesn't affect the flow. So we can set it like a symmetry, or like in Fluent we will do as a slip wall. So no shear stresses on the flow. And then the far field is the last one. We insert boundary far field. And this is either a slip wall or a symmetry. You can set it like a symmetry, so that doesn't affect the flow. And we select this top surface. When you do this, now you have defined all the boundary conditions for the geometry. So in order to create a file that is compatible with Fluent, you should create a def file. The def file stands for definition file. We don't need actually to set all the other information in Fluent because it will not be transferred. We don't need to set them in CFX as they will not be transferred to Fluent. So we can just push that define run on the top, and then you can see this def file. So I call it with the same name of the mesh.
Sorry, where we can find the meshes again? I overlooked it. Sorry.
So the initial file is in a that link that you can find in the PDF in Moodle.
Okay.
There is a link that will open to this the test case description, and then you have these links where you can find all the files. You can choose which one is better for. We are using also structured version of grids. It means that the elements are structured. And okay, this is the definition file for CFX, but we don't want to run it in CFX, so we are just closing this. You can also close this CFX because we have what we need. There is this def file. It is the same that you can actually download from Moodle. So this was just like the how I got the def file. Okay, so now we can start using Fluent. Now we have this def file. And before starting, let's see what we should do in Fluent. So what we are asked to do. In the exercise here, and this is also actually the homework, they are the same, so once you finish this exercise session, you will also have the homework ready. You should compare the CFD results to theoretical results for wall screen friction coefficient for different Reynolds number based on theta, where theta is the displacement thickness, and then the law of the wall at Reynolds theta equal 10,000. Also, you should plot the eddy viscosity at different locations. Here you have some definitions. So for Reynolds theta, how it is defined. Here infinite stands for the free stream conditions, so farther away from the solid wall. And this is also the definition of theta, the displacement thickness. So where close to the wall, we can calculate the distributions of density and velocity. And then we should solve the integral. Of course, we'll solve it as a sum for each value in the cell that we are calculating. So let's get back to this website. And okay, here you have even some more equations. So Reynolds theta, so Reynolds number based on displacement thickness, definition of displacement thickness. CF is the screen friction coefficient. So it's the ratio between the wall shear stress and 1/2 rho infinite times u at the power of 2 infinite. Definition of wall shear stress, and then y plus and u plus for the law of the wall. Then on the bottom of the page, we also have some theoretical or experimental data that you should use to compare your results. For example, here we have distribution of Reynolds theta as a function of x. So where x equals 0 is this point over here. So this is x0. This is our reference frame. And you can also find the values of this chart. So there is this dot file where you can find two columns, where you have on the left the x in the left column, and on the right column is the Reynolds based on theta. Then you have also some other charts and data. For example, you have the screen friction coefficient as a function of Reynolds theta. And also in this case, there is a file here, text file, Reynolds theta versus CF. And then there is also the law of the wall, so U plus versus the Y plus. And also in this case, you have a text file for measurements of theoretical data, depending on the variable. And you should compare the results, and I think let's see. Yeah. Then here you can also see what to expect. There are different turbulence models. You haven't studied this yet. Now we will simulate this case with the mixing length, and we have nothing here for the mixing length, so we can actually compare our results with what to expect. And so yeah, the results that we get with CFD, we should then compare them with this. So I think we can, do you have any question about the test case? If no, then we can start the setup. So I'll open Fluent. Depending on the version, there can be some typically minor modification, variations of this interface. So then, but what you need to set is the dimension is 3D. Then you need to set the solver options, and typically run double precision. Solver processes, this doesn't really matter. This is a simple case, not computational demanding, so I use 3 processes. And then you should set the working directory. So the working directory should be the folder where you have your def file. So I just copy this path into my working directory. And then I can launch Fluent. I'll just take the same file that you have in Moodle, so I will not use this def file, but I think they should be the same, but I don't know if I made some different namings of surfaces. Okay, so now that we are in ANSYS Fluent, you can import the mesh file, so that def file, using import CFX definition file. So in this way you have, you can import this def file. And in this interface, now it's loaded, but you can also display it in this, using this this command over here in the general tab. It is display. You have the surfaces that you want to display, and then the options is faces. I will also plot the edges, so the grid, the mesh of the geometry, and display. So this is how it looks. So that's correct to read that there is an inlet. You can see these blue arrows, and there is also outlet with the red arrows here. Where you can see a finer grid here, we have higher resolutions of elements because we want to solve in details when the flow is approaching x equals 0. Do you have any problems with? Yes, please.
Can you show once again how did you put this on the screen?
Yeah, in the general tab, if you double click here, you have this general mesh display, and there you can select the surfaces you want to display, so all of them, and the options. So you can plot the faces, but as well as the edges, that means the grid of the geometry. So in general, we can set some solver options, pressure-based or density-based. Typically, pressure base is for incompressible flows, density base is for compressible flows, but it's not always the case, I would say, depends on the cases. By the way, in this course we'll always use the pressure-based solver. Time, we can choose either steady or transient. This is a steady case, we'll get a steady solution, so we go for the steady, so we don't change it. Then, what we could model first, so in models, if you expand, if you click on the plus, yeah, you can see that there are plenty of models. We don't really need to look at all of them, we just need to look at the viscous model, that is the turbulence model, and the energy in some cases. So in this case, we have an incompressible flow. The energy equation, it's not really crucial to solve the flow, but still, I typically use a flow formulation that includes the energy equation. So I go in materials. So if I double click on materials, I'll get here the materials for the fluid, that is air, and the solid, that is aluminum. We don't have any solid part. I mean, we have the plate, but that doesn't really, we are not really solving any equation for the plate. So we are just focusing on air. If you double click on air, right now it's set as a constant density and constant viscosity fluid. So like the simplest way to model air. What I typically do is setting the air, so if you click on density options, instead of constant, I set it like an ideal gas. So I'm solving the equation of state for an ideal gas in a way that the density is a function of pressure and temperature. When I do that, you can see that now there are also other properties that are appearing, like CP, thermal conductivity, molecular weight as well. And that's because when I hit change create here, so I change its density to ideal gas and change create to apply that. What happened automatically is that now the energy is on. That's because you need the temperature to solve the equation of state for air. Okay, so once we have set the working fluid, so we use ideal gas here, then we can set the turbulence model. So as you can see, if I double click on this viscous tab, here we have different type of models. So in viscid, that means we don't take into account the viscosity forces. Then we have laminar and the other turbulence model. We use Spanlar Talmaras from next reversal. Then there are two equation models, so other models that we will study and use later. But now we need to solve it as said in the exercise using the mixing lag turbulence model. We don't have it here, so we need to enable it. And we can do that if I close this window over here. In the console tab, so at the bottom, there you can follow this path. So you should go in, you should write define, enter, then models, enter. I will write this also at the whiteboard that you can follow the path. Then viscous. And in viscous there is, if I click enter, here I can see all the options. And there is an option written mixing length. So we copy this and enter. And then I'm asked if I want to enable the mixing length model. And I say yes. So the path is In the console, you write